recording now, and I will upload it. I don't know if I uploaded last week's. If I didn't, I'll upload last week's as well. Okay, so slight word of warning. I basically haven't slept over the last 3 days. I literally did not sleep like 2 days ago or the day before. And I only got like 5 hours last night. So that happens when you're really busy. So if I'm a bit out of it, that's why. And still pretty good. I managed to go for a cheat yesterday on like no sleep, so I should be okay now. A bit of sleep. Yeah, so the rough idea of this stuff today is we're going to start off with just some memory label stuff. Figure out what memory address is for each label. Question-wise, this could show up in the final exam. I would say it's pretty unlikely, mainly because typically if we give you MIPS questions, unless maybe it's a multiple choice sometimes, I guess. But typically we'll just give you like an actual question to fill out that will show this, rather than like having this kind of weird like pseudo state where you kind of have to like fill out the memory addresses and figure them out. We'll just get you to just like write a program that uses this, right? That way, if you write a program that uses it, it's the same thing, and it also kind of gives you more flexibility to actually know whether or not it's correct. Anyway, so to begin with, we have text and data. So text is for code, and data is for, I guess, data. That's kind of a bad way of saying it, but that's effectively what it is, right? So text it's just, I think it's a pretty old thing, probably like earlier than the 60s, 50s, probably like before computers really existed, and you kind of had this like the origin of like lambda calculus and stuff. It's probably where text comes from. If you look back, like, we're talking about like Grace Hopper, kind of very old, right? It just always kind of meant like code, effectively, right? Code wasn't really called code for a very long time, I believe. I believe it took quite a while for people to start calling it programming and coding. So it's probably just referred to as text. I really don't know. That'd be my guess. Data is just for basically anything that you want to be mutable. So it's kind of like global variables typically. As you can see here, like these would be globals. It's not necessarily just for that. It can also be used as like a pseudo malloc in some cases, and we may come and talk about it today. It's not something that you need to know, which is why the reasons why I say may, because it's really kind of annoying to use. But there's like probably 10 to 15 cases where like solid cases in this course where you may be able to use it, where it makes things easier. The thing I'm talking about is called SBERC. It basically allows you to expand the data segment. The big reason why that's awesome is it means you can basically think of it like as malloc that you can't free, right? So you can just expand it to get the memory that you want, then not have to worry about freeing it. And the best part about it is that and sometimes called an arena allocator, right? An arena allocator is something that you just allocate a bunch of memory, then free all at once, right? The reason why that can be cool is because with a stack, you kind of have to keep the push and pop, right? But with this, because you can't free it, it's just out there in the open. And even if you could free it, you could still try to have something that goes on top of it and like manages what chunks are freed and what chunks aren't freed, and like you reallocate if it's like along one of those chunks, and if it's along none of them, then you can use SBERC at the end. It's really annoying to write and takes quite a bit of effort, which is one of the reasons why we're not doing it. There's many other reasons too. That's really the main reason. Maybe like in 2 weeks' time when we cover like system programming in a bit more detail, we can come back and we can write like malloc MIPS. It's just not an easy thing. It used to be an assignment to write it in C, and people would struggle with it. So it's just annoying. Anyway, so data is kind of really just used for globals in our use cases. There's also word, space, ASCII, ASCII-Z, and byte. These are like modifiers, I guess. I believe they've got an actual name. It starts with D, but that's not really what I'm talking about. A directive, but they're not really direct. They are directives, but like that's just everything's a directive. Like all this stuff is directives. But they're effectively just storage modifiers, right? So you're specifying how large the storage item is, how many storage items there are, and some cases also you're talking about alignment of those storage items, right? And so last week, one of the things we looked at was this kind of really annoying final question in the Kahoot. I don't know if I've got a copy of it in the document here. No, I didn't. And it was all to do with the size of that struct. I don't know if you remember, you had like a union, and we were asking what the size of that union was. And one of the things is when we're calculating the size of this union, it was quite annoying, right? Because you basically had it was quite annoying because you basically had a union that was composed of like I think it was an integer, a double, and a struct in another union, right? And that double meant that the whole thing had to be an extra 4 bytes, right? Instead of 12, it was 16, if you kind of remember. Maybe I can like write up an example. Okay. So what we had is we had a struct, language mode. Here we go. Struct. I think I called it K. It doesn't really matter what the name is, right? And inside of this, no, it's a union. So it's a union. Okay, inside this we had an integer level of a struct that contained, I think, 2 ints. Then, excuse my bad naming, and then another union which contained, I think, the exact same thing as above. If not, maybe slightly different. These don't really matter. No, it wasn't this, was it? It was like this. So what this was we had 12 bytes due to the struct, right? And so this is the largest item inside this union. So people were thinking, oh, it's 12 bytes, but it isn't. The reason why it isn't is because this double here, right, forces everything to be aligned on 8 bytes, which basically meant it couldn't be 12, it had to be 16, right? Because if you have 2 of them in a row, you want it so that they go tip to tail, and such that each of them is aligned on that 8 byte boundary, right? And so that was a really tricky question. It's not an easy one. And so alignment's kind of quite annoying. And so this course doesn't really deal with it in a nice way. And that's kind of good because one, it means you don't really have to know it because typically the questions we'll ask don't really require it. I don't know what question I want to do first, but it is kind of important to know. And so the way alignment works is if we go to the actual MIPS perspective, so you can actually see kind of the definition of it in terms of the context of the documentation. And so when you're looking at it later, you know what you're looking for. Have they changed these resources now? Okay, so they've got this here anyway. So we want to look for directives. Here we go. We want to look for line. So line talks about the next datum. Now, datum is a fancy word for a single data item. So it's just like an old-timey word. I would probably say that data is kind of singular and plural at the same time. Like you first data or multiple datas. Perhaps, but like in the old times, it was datum and data, right? I think some people still do this and call it separated this way, but most people don't bother. Okay, and then the next thing here is if it's throwing for appropriate alignment by inserting enough padding for the item such that a half word, it doesn't really talk about it, but basically such that it's a 2 to the power of this n, right? So we can see here, a line 1 requires 2 bytes, so it's 2 to the power of 1. This requires 4 bytes, so it's 2 to the power of 2. And this requires 8 bytes, so it's 2 to the power of 3. So this is like the power, or like the bit position that you want to align to. So it's been annoying in that regard. And also a line 0 isn't actually always 1 byte. Yeah, line 0 has some weird behaviors around how it aligns. Anyway, so you really don't have to care about that, except for when you're seeing stuff like this, align 2. What this means is that this must be on an address that's at least a modulus of 4. If it isn't, it's going to like add padding so that it is. So in this case, we're like finding this out if we put this on one side and not do that, just do this. Oh, they've changed this file. Oh, so fancy. And that's not what I wanted to do. It's fine. I'm just going to do it manually because no point mucking around with it too long. So we're just going to put this on the side, and then we're going to put the memory labels on the left-hand side. And then this will update the actual automatically. And so what we can do is we can just fill out this stuff. So we've got A, B, C, D, E, and F, right? And we're talking about like each of these sections. Right? So the first one is A is 42, right? Here, which is actually 2A in hex. And that's just located on address 0x100100020, right? And the same question as this one here. And so the next part is, well, what's B? Right? So if this is an int, which is a word, then that mean that the next one has to be 4 bytes longer, right? So it's going to be 4 bytes long, right? So I'm just grabbing something up. And the 4 bytes long is kind of, because this is 4 bytes large, and therefore the next address must be just +4. guess. There's a better way of explaining that. It's probably just to say plus 4 because this is 4 bytes. And the contents of this is going to be space, which is just going to be nothing, which is just going to be random. Like it's whatever was there, basically. Right? It's not going to zero out. And then we got C, which is an ASCII. This is located at plus 4 to this because it's got a space of 4 bytes. And the ASCII consists of multiple characters. This is where it kind of gets a bit weird, right? Because how the contents of this is going to work is going to have A followed by B followed by C and followed by D, right? And this is going to be kind of like one section of it. You have to do like a backslash or something weird like that. All right, it's fine. And then the content in hex is going to be, well, 65, 66, 67, 68, right? All in hex, right? Which I mean, it's not that hard to do off the top of my head. It's just going to be OX, 1 for 60, for 64 rather, 32, 16, 8, 4, 2, 1. That's wrong. And then just convert X, it's fine. We'll convert X. So this is just 1, and then this is, well, it'll be this, right, which is going to be 4. So it's going to be 41, I think. 42, 43, 44. This is less important. I'll make sure it's right afterwards. So the next step is just add 4 to this. I'm just aligning these in 4-byte chunks because that's really how it works in most of the MIP systems. They're aligned on word chunks. Like you really shouldn't, like you could put this on one line, but it's nice if you don't because it allows you to see some things. So for example here, we're just going to have E followed by /0. Then we're going to add a slash at the front. And that's this chunk here, which is going to be OX probably 45 followed by 0. And when we're storing it here like this, the thing is that there's actually got to be 2 extra bytes afterwards because of the alignment here. So the alignment here means that this has to be aligned on 4 bytes. So if we just add 2 bytes to this, right, we get OX 10010002, and then C goes to D, which goes to E, right? But the problem with this is that if we grab this address, structure in whatever your favorite tool is, I'm just going to use Python. You can see when I was using my assignment like 2 days ago. And then we can do this modulus by 4, get 2. Right? So it's not actually divisible by 4, which is problematic. But the difference is it's not divisible by 2 because there's 2 remainder. So we're just going to add 2 extra addresses to this. Just like this. Now it is. And so now this is going to be allocated on F, and then 0. Also, properly, 61. About the man ASCII table. Just thinking about it in my head. Could have also been right the first time. Freaking yeah, 61. 62. Cool. I think the other one would be the uppercase. Yeah, 41, 42. So I was still writing both ways, but we'll make a match to the other one. And this one will be 65. So, well, and that's actually an interesting aspect of how the difference works between lowercase and uppercase characters. Is that you'll see about uppercase characters is that they have, OX40 is basically the range. And then it goes up a bit more, but that's still kind of within the range of OX40. And then A is like 60. So what happens is that you can actually just toggle, I believe, a single bit. That single bit, or maybe 2 pairs of bits. If you do like an XOR with it, it will allow you to switch between uppercase and lowercase. But you can't do that always because obviously if you have characters that aren't ASCII, like aren't like alphabetical, then that will run into issues if you do that swap like that. Anyway, let's just keep going. So 1, 2, 3, 4. This will just be 1, 2, 3, 4, but in hex, so it's going to be this. And then what's next? 1, 1, 4, and this is going to be plus 4, and this is going to be interesting thing about this is that we have 4 bytes after this. That's what this is saying. So each one because it's aligned on 2 bytes, only the first one gets aligned on 2 bytes, and the rest just go right after each other. So this one here gets aligned on, say 4 bytes or 2 to the power 2, and then the rest of these just kind of just carry right after each other. They don't have to worry about the alignment. Just like this element itself has to be the first one. The next one, each one's a word, so each one's going to be 1 byte each, like this. Then this becomes 3, D, E, F, 4, 0, right? Is this possible? And the final one is a space, which is just going to be 4, and who knows what's going to be in this memory address. And this is going to be this. Right? 3, just to keep the standards, and same thing up here. And I will also add. I like I use 3 here, but that's okay. So that's it. And if I save this and then reload, I believe it will automatically update unless its cache is invalidated. Anyway, so it's really not gonna. Cannot read property links of undefined. Fix it up in the tree. It's probably just because I added I was adding these answer things here, and so when I pushed it, I probably also pushed these answers. And if the files don't exist, Wk5 then it gets crazy and it gets cranky. String.s, yep. I'll probably just fix this afterwards rather than trying to fix this now. Max.s, yeah, that's fine. And mental break. Yes, that's okay. I don't know which one's fine. Anyway, it's fine. I will just comment these out and then repush. Fix it. And I'll come back later and look at actually properly fixing this in the lab for the first like 5 minutes. Okay. Meantime, we don't really need to. So the next thing that we got to talk about is like the assignment, right? So the assignment's coming out soon, and we're going to be doing a bit of an pass on working out how main memory works in MIPS, because it's probably going to be relevant for the assignment. Because most likely, I believe that's can't remember, it's a simulator for MIPS effectively. That's at least what we're instructing us in the meeting. So that means you're going to be writing a subset of MIPS. It's a very small subset. They've made it smaller every year. I did it when it was the first year they did it, and it was a very large subset. Almost every instruction, and we had to do a lot. And it was pretty easy still. But the problem was it was really easy for people or really hard. Because there was just so many instructions. If you're like, yeah, this is fine, let's go do one by one, and like they're all pretty straightforward to do, or you're like, oh, this is so many, and you got really overwhelmed and confused. But it's okay. This year will be easier. There'll be a lot less of them, so it won't be too bad. So what we're going to talk about now is talk about each of these memory allocations and talk about what do they do. Each of these load addresses and these store addresses and load words and store words. So importantly, what do they do, and also is there any like issue with it? Is there going to be any problems and so on? So to begin with, we have something as simple as this one here. So we're saying load the address AA into T0. Now, if we look at what happens when MIPS actually grabs this instruction, right? This is a virtual instruction or pseudo instruction, right? So what it's going to do is it's going to convert it to an actual instruction behind the scenes. And so the way it's going to convert it is it's going to go, okay, well, really all I want to do here is load the address of AA. So first off, when the assemblers can come along, it's going to patch AA, right? So it's basically just going to say A is going to be some kind of address somewhere, right? And it's just going to be a number. So it's actually going to basically do a simple load immediate effectively based on the number of AA. So say AA is 404, right? That's going to effectively what it becomes, right? So what it starts off is it starts off with this idea. Now LI is also virtual, so it actually becomes something like an LUI to load the upper part of the word. So what this does is loads the upper 16 bits. Say that's 0, and then it will do an XOR to load the lower 16 bits, which you get say are 404, right? So this way you can kind of have the upper and lower parts of each of your data members set, right? So this is what it does for every LI typically. You could do an add as well. It's always a little faster. And actually, it shouldn't be a XOR. I think it just is maybe just an OR. It really doesn't matter unless the data member has stuff inside of it. If the data member has stuff inside of it, you have a problem anyway, because like you're just going to be ORing it with it. So it really has to be 0 before any of this occurs. So I'm pretty sure that's okay. I presume they would do like an AND T0 with 0 if they really wanted to 0 out, right? That'd be the easiest way you could do it. It'd be basically just zeroing the entire set out. Okay. Doesn't really matter though, as long as it's all filled with zeros beforehand, an XOR will work. Okay, so what things it doesn't know it's 404 yet. So it does something called patching, which is something you really don't have to care about, but basically it just inserts this kind of like random sequence here that consists of the same number of bits, and then it makes a writing in a different file called a patch file. Typically, it may do things slightly differently. If it's not meant to be fast, it may just literally go looking for it. But if we're talking about real assembly, it won't. And the patch file basically is some kind of like external file when it's assembling this to actual executable code. Like when the compiler is doing it, for example. So the compiler creates a linker, which then links all your code together to actually create the output. And this linker will go through and create these patch files, right? And so what it'll say is okay, byte address, let's say this is byte 12. Well, I guess each one's going to be 4 bytes. So, 4, 8, 12, okay. And then inside this byte address, we're going to say, okay, we need to update a sequence of bits. Let's say we're updating, I don't know. In this case, an OR command can be encoded as an opcode only. Yes, so it will be, I believe, it doesn't really matter. I would say only. It's going to be 8 bits for the opcode, and then 5 bits for the first register, and then you'll have a second register as well. So that's 10 bits, which makes it 18 bits. And this will consist of an immediate value of 16 bits. So I believe, off the top of my head, it will probably be like 16 to 31, maybe 15, doesn't really matter. And then it will say, okay, I want you to patch this with something, right? So what this means is I want you to find when AA exists in this file. So when it goes through and finds the label AA, it will go back and patch this address or this location here with the value of AA. So when it scrolls down, finds AA, goes, okay, this is located at address 404. It goes and tells the patch file this is 404. And then at the very end, it will go through and patch the entire program, right? So typically it patches retroactively rather than as it goes, just because it's slightly faster for the linker that way, because it means that you can create like multiple patch files and apply them all together at once, rather than having to like kind of constantly modify your file over and over again, so you don't patch something twice. I guess it doesn't matter if you patch something twice. Anyway, so this is just going to load the address of A, right? It's just going to find whatever A is as like an integer, its position. The position of this instruction or this directive or this member. That you can do it for anything. You could do it for like a data member. Like it really doesn't matter. And if you did the account exercise, you probably did this, right? You created like some space, so let's say 4096 bytes in your text segment. This is your text segment here, like, there's an implicit.text at the top. And you created some 4096 bytes in that text segment for code, right? And so therefore you can insert code and write code directly inside the project itself, right? So basically the program writes code for itself. It's like self-writing. And you can do that. You can modify instructions. Now, typically, we have something called there's a bunch of things that prevents this. I'm not really going to go into it, but at the end of the day, it's kind of like a permission level thing on pages. And so you would have like your text page here, right? And in that page, it would turn off the ability to write to the page. Right? It's just that Spim doesn't. So what that means is that you can not write to text code. Otherwise, it's a big security risk if you can suddenly change the code that you're writing, that you're running. The next thing is LW. LW is for loading a word from a location. So the location here is AA, right? And so when we say load word, actually it's going to grab 4 bytes from that AA and chuck that into T0. In this case, it's going to grab A, B, C, D and put it into T0. So it's going to be 61, OX 61, OX 62, OX 63, and OX 64, right? The next step is LB. It does the exact same thing, but with just 1 byte. And then we can do a bunch of craziness around this to basically allow us to write more complicated addresses like this, where we can add constant numbers to it. This has to be constant. And obviously, the reason why we can add constant numbers to this, as I maybe hope people can see, is that the system can kind of compute that at like runtime or compile time, sorry, assembly. Because as I said, with that patching, right, it's not that hard for us to do some simple math with it. Now, I believe that some of these are only SPIM because I'm trying to find one for x86 that's crazy, because x86 is like much more of these like craziness where you can kind of do stuff for addresses. Like you can, for example, add a constant multiple of like 4. It's called like a Leah instruction, just to show you kind of what the idea is. Okay. It's not correctly. That's more like a very simple example. I was good at images, I guess. Anyway, so this is fine. It will just add 1 to the address, but how the like +1 works here, right? It's literally just gonna add. Right? So for example, sorry, my mic just got like a connector thing to it and it gets hot, and then the mic goes crazy and drops out. So what I was saying is here is gonna add 1. We could do like LW and like +4, for example. Then that would allow us to go to the next segment, which would be B here. And in this case, there's not that much craziness to it, but there are more languages that have like more crazy versions of this. In our case, we can really just add constant multiples of things. It's not too bad. When we do something like 8 to here, right, it's actually going to grab the value inside T1, then add 8 to it. So this has to be done like at runtime when the program is executing. So we can't just like do like +8. And so this allows us to add constant offsets. For example, you have a structure, right? This could be like your second data member. So you could have like 0, 4, and 8, right? So 0 would be like the start of the structure, which could be like an integer. Then 4 could be like another integer. Then maybe 8 could be another integer, like X, Y, Z for like a vector or something. And again, this is just going to load a single byte from this address and load a single word. The only weird thing about this one here is that when loading a word, you have to load 4-byte alignment. Like your thing has to be 4-byte aligned. So when you do something like this, it's actually going to result in a memory alignment error because you're accessing unaligned memory. And this is what we were talking about before, right? So when we're accessing 2 from T1, right? So that should be probably 2 from T0. And same with this one here. Otherwise, it really cares. And so when we're accessing T0 and T1 here, right? Or while at T0, we got to think about like where it's going to allocate. So if we're going from T+2 from A, which is really what this is saying, we're going to go here to A, and then we're going to go +2. So 0, 1, 2 at C. And the problem with C here is it's actually not going to be aligned to 4 bytes, which means that when we try to access it and we try to load a word, we're going to try to load basically C, D, and E all at once, and F, I guess. And MIPS doesn't like the fact that we're accessing that memory and it's not like a 4-byte chunk by itself. It's not like a aligned 4-byte segment. And so it's going to complain. Some languages like x86 won't complain, instead will just be really, really slow in some cases. Like there's like a performance penalty for it because it has to like, do a lot of work. Some languages will like fix that up and do other stuff with it. And it completely depends on in terms of like what you're trying to do at any point, right? find this example that's really nice. You can do some craziness with it. Like you can, for example, go like 2 to the multiple of like some kind of constant value plus some other kind of value plus some other value. Multiply the whole thing by like some multiple of 2, and then there's your value, right? Multiply like some address per multiple. So we'll actually do some very complicated instructions. So that's the whole point of like x86 and stuff, is that you have some very complicated instructions that you write code that's pretty fast, right? But they're very complicated and there's a lot of them, right? But something like MIPS tries to simplify it with very few instructions, and each instruction has like a single responsibility. And you don't have things like move, you don't have things like LUI, LI and stuff, right? The idea then is that for all your instructions the same size, right? As x86, every instruction can be a different size, and size can depend upon like the arguments, and it gets really complicated. Anyway, so there's a breakpoint. Breakpoints are what we talked about a bit last week with the SPIM, right? You can like left click on like the left side, and you can set a breakpoint, and you can step through the code one by one. And they're useful, and it's just annoying to use in SPIM because SPIM can be a bit of a pain, but they can be useful in some cases, right? Maybe try it out this week. Get some help if you need to figure out like how to use it properly. Anyway, so now I've been blubbering on. The site's probably back up. Okay. So we can close this down. I'll fix the answer thing. It's maybe because like some of the files are empty. I don't think it likes if the files are empty, because I think when it tries to import them, it complains because the files have nothing in them. So we're just going to do one question, then we'll come back and have a break for like 5-10 minutes maybe. Just because we're probably going to go over time by like 15. Just because I'm tired today as well. And the break will just be like thinking about a question. So you can go off and do something, get some glass of water or something. So long multiplication is the only thing I really want to talk about mainly here. So long multiplication is the concept of basically doing these quite large numbers here and multiplying them together, and the result x is going to be very long, which you can see here. And so it's going to be 8 bytes, right? And so it's going to be quite a freaking chunky, right, thing. It's going to be huge. So in MIPS, it's very annoying to use, right? Because MIPS doesn't like your like large registers. You can only have 4-byte registers in MIPS. And so what we can do is we can kind of cheat. We can basically have 2 4-byte registers that we act as one. And this is effectively what floating point arithmetic does in MIPS. Like floating point registers and stuff is that they effectively use 2 registers. In our case, we can do the same kind of thing. And so there's a high and low register, right? It's implicit. You can't actually access the high and low register. It's like completely unavailable from you, but you can use instructions to access it, right? But I can't just say like $high, $low. Right? You have to use instructions. So in this case, for example, we're basically just doing the same code here. We're doing a syscall to basically scan f in a number, and we're storing that number in y, and then we're loading from y. I guess this doesn't really matter, just for semantics reasons, right? Then we're going to add 2000 to it, and then we're going to load from y again, probably not needed, but for semantic reasons, I'm making code match what like a simple version of what the C is as much as possible. And then we're going to add 3000 to it, and then we're going to multiply them together, right? And what we'll notice here is that there's only 2 source registers, there's no target. The reason why is because the target is high and low, right? And so it puts in high and low, and we can access the high using MF high and the low using MF low. I want to say there's one instruction that lets you do a multiplication and a division, a division and a modulus at the same time. I want to say that's how the div command works, is that like it puts the division in one high register and the like modulus in the other register. I'm not 100% sure. You'd have to look at it. I typically don't recommend using that. If you want to do like things like modulus and division, just use like the rem commands and so on. You find it here, rem and div, rather than using here I was right. There's low and high. So if you just use div by itself with 2 registers, it will use low and high. You can use low and high to access those. But honestly, I just recommend just using these. It's the same kind of thing, and it's much easier to use, and you don't have to worry about performance. You're just trying to keep it as simple as possible. Anyway, there's a bunch of other instructions too that you don't have to worry about, like basically everything here about sign extension and like counting leading zeros and leading ones. Like if you look in the earlier tuts, you see I use some functions that are similar to this, especially in the first or second tut. But again, stuff is not good. Like just keep it as simple as possible. It's pretty nice how it tells you everything about address exceptions and so on. Anyway, let's keep going. So the next step is, I'll just save the bookmark, is to look at arrays. I don't know how much I want to go through functions yet. So I was told that you guys haven't actually covered functions. How true is that? Because if you haven't, it's going to be a bit of a rude awakening if we do it today, because today was going to be quite a complicated function example. We're going to go through Fibonacci and then build a linked list in MIPS, which is a bit of a pain. Anyway, so let me know if you've done, yeah. I'm still going to do it, but we'll go slower and we may not get to the linked list. We may just do the Fibonacci and then we'll do the linked list next week. I think it's not that hard to understand, but it is more difficult. Anyway, so we'll take a break now for 5 minutes. I'll leave this question up just so I can get some water and relax. So I'm very tired. And then we'll come back. And so in the meantime, you can think about doing this question here. Basically, just trying to validate this thing as few registers as possible. And then I can ask for some solutions if people have them. Else we'll just talk about a few of them. And so as few instructions or registers as possible. I think you can using 2 registers is fine, but then you have to use a stack, which is more annoying. We'll talk about the stack today. I mean, you don't really have to use the stack. You can just use like a data member and just like write from into it. But in this case, really, you can do it in, I think, very few instructions. I remember getting it down to quite a few. I did get down to, I think I got it down to 9 instructions. And then I think the course has a few solutions that gets down quite small as well. I think the smallest instruction one was 3, 6, 8. There's one with 8, but that one has some other things to it, I think, that makes it slightly different. Anyway, we'll look into that in a few minutes. Okay, it's been about 4 minutes. So I'm just going to open up the break and kind of look for it, talk about the versions of it. Okay, so the solution for something like this is that we want to start with a simple interpretation of it, and then we can build up. So a very simple version would just be to try to do one by one and process left to right. So in this case, we're going to store them each in separate instructions, in separate registers rather. We're going to store X, we're going to store Y, we're going to store Z. Right? So this is X. Yes, we probably don't need to write this, Y and Z, right? And then what we're going to do is we're basically just going to break each of these sub-expressions into individual variables. We're going to store, and then we're just going to add them all together, right? Kind of. So in this case, we're going to store the result of multiplying X by X, right? So we're going to store that in T3. Let's push these across a bit so they line up. So X by X is in T3. Right? Repeat it for Y squared. And for Y. This is not going to be a performant version, but we'll write a better version later. I'm just going to call it first. And then the next step is to basically just add them all together. So we're just going to add these three all together. Obviously, you have to subtract this one, but it's not bad. This is going to be adding T6, T3, and T4. So adding these together. Later, do this X squared plus Y squared. So just kind of accumulating all these things together. But then we can subtract from T6. We're going to subtract T5. Subtract T1. We say accumulator minus or equal to Y. Then finally, just going to multiply this by Z. So effectively, we're doing it one step by a time, and we're kind of building up. So the one step by one step thing here is that effectively we're loading all these words in, we're multiplying them, and then we're adding subtraction line. So the strategy to reduce registers and to make it faster is to begin by trying to think about what things you don't need at the current moment. So to begin with, we don't need Z yet, so there's no point loading it yet. Only load it when we need it. The reason why is because we could reuse a previous register, right? So we don't always have to reuse the same register. So for example, when we're just down here, in this little context here, all we care about is T6 and T2. So we don't have to use T2 here. We could just use T0. Reuse X. This is register. And once I go through all these, I'd be interested to see what you guys have written. So in the meantime, you can just check in the chat if you've written one of this, and we can talk about like whether or not you've done anything to optimize some of them. This is going to be just like a breakthrough of ways you can optimize it. If you haven't, don't worry. It's really meant to just be a break. Some people are breaking, so it's nice to put something in there for those people who actually want to do something. You can't waste it for 5 minutes. So with X and Y here, which we're loading, we need both of them immediately. And so the strategy here is to, okay, we've loaded this into T3 here. But once we've loaded this register into T3, you don't really need X again, right? Or more specifically, we can reload X for this. That way we're using less registers, right? So what we can do here is that we could begin by effectively computing y squared, chucking this into a variable, or computing x squared, chucking this into a variable, and then computing this and replacing x with this. That way that we don't have to have an extra register for this. So basically, if that makes sense, I'm kind of saying use like T2 for this, for example, T3 for this, and then we can use like T0 for this. We don't need T0 anymore at this point. And then to add them together, nothing really changes, right? But now when we're adding them together, we can use T1 to add them all together, right? Because we no longer need T. So we're adding T0 from here. We're adding T2 and T3. Add these together. So this is T2, T3. Then we're subtracting T0 from T1. Then we're adding to T1. Applying to T1 this, right? And so this version will be 2, 4, 6, 9, right? So that's pretty good. And we only ever use 4 registers. There's still quite a few registers to use, right? So we can actually optimize it down to just 2. And so the way we optimize it down to just 2 is to be even more clever. So at this point, we're basically only ever going to use a register once, right? And we're just going to kind of reuse it over and over. So we're going to begin with our x times y. And it doesn't really matter what order you do this in. But I'm just going to basically write it like this. I'm going to grab my expression here and say y times x. And go x squared minus this, because these don't have dependencies on each other. Like I can calculate this and then place x with this and be okay, right? Like I can use 2 registers to compute this, right? No, unless it's necessary. So reusing registers are good if you no longer need the variable. But just because like you can go, oh, I can write this in a super way, doesn't always mean it's readable. Like this code here won't be that readable. So you should try to avoid it if you can. In some cases you can't, or in some cases you want performance reasons. Yeah. Like even in professional code, they're not going to just go crazy with reusing all the registers unless like there's a performance reason why, or it don't have enough registers, right? So in x86, for example, there's a lot less registers to use. I think x86 only has a couple, maybe like 5 or 6 general purpose, and then the rest are just like really mainly stack based. And there's a few for like checks and balances, like checking whether or not something has like passed an if statement effectively, right? So you have like a confirm and so on. Yeah, performance really doesn't matter. We care much more about your style. So just try to, and typically you will never be able to write good assembly code anyway, right? Like even once you've been writing for many years, the computer will probably beat you every time, just because computers have a lot more years of experience than even like someone who's been doing it for 5 years. Maybe able to beat it in like very small examples, like very, very small, like maybe like 30 lines of C, maybe 40. As soon as you get to like a couple thousand lines of C, you can't keep like that performance benefit up. Anyway, so we have x squared minus y squared that we're going to compute. So we can use you can reuse the x register for this. This can be T0, and this can go into T1, right? Okay, so in this case here, what we're looking at is we're trying to go, okay, let's reuse the registers here. So we've got x and y here, and we're going to basically go multiply x squared by x squared and chuck it into x, right, like this. It's kind of like saying temp1 equals x squared. Before we do that, we're going to do our x times y. Right? We're going to load this. Wait, let me not edit the actual example here. It's okay. I've actually got like it written out properly, and I'll just revert it back to that afterwards. I kind of like editing in place. So we have x squared times y squared that we've got here. We're just going to bring this up here, and we're going to track this into 1. Right, so we're reusing for this one, and then we're using 0 for this one. Right, and so now we've actually got quite a nice solution here. And so we can go like For example, we can actually compute this part. We can compute this part and chuck into T0. Right? We no longer need T0 anymore. And so basically it's just going to subtract T1 from T0. And so this is just going to do x squared minus. But the next step is to basically load our y again, right? So we're having to load y again, right? But the benefit is we're using only 2 registers, right? So it's okay to load things multiple times if we're really doing high performance stuff. Typically, the loading will be more costly than just multiplications, because loading same from main memory, unless it's immediately in the cache. In this case, it probably will be in the cache, so it probably will be fine. But it's just like kind of a costly procedure. It can take a lot of time. I'll go through it in a second. Anyway, so we're just going to do y squared. Then we're basically just going to add that to our accumulator here. Which is adding up all our values. Don't care about any of these. And then to do z, we're just going to load this back into T0, or probably into T1 actually, right? Because we're already using T0. They can just multiply T0 by T1, chuck it back into T0, for example, right? We don't have to use T0 anymore, right? So this would be probably the most optimal in terms of instruction count. I really doubt you could get it below 2. You kind of always need 1, like to like store. Like if you're going to be timesing 2 things together, you probably need 2 registers. Maybe you could try like cheat, like abuse the stack, but like I really doubt. And using the stack anyway, you could be using SP, which is a pointer, which is a register. So it's regardless what solution you come to, you're going to be just using 2 registers. I believe there's other solutions as well being discussed. As I said, there's one that I think is down to 8 instructions, which is pretty incredible. But I believe that 8 instruction one uses 3 registers. So anyway. And the way it uses 8 instructions is basically it just loads this into, for example, T2, right? And so once we load W1 to T2, we don't have to do the second load here, and okay, right? So that's how they got to 8 instructions. I personally don't like that. I think it's nicer to keep fewer registers, but it really doesn't matter what you do, right? Okay, so I'm sort of saying whether or not I won't go for functions in much detail. So what we're going to do is we're just going to begin by like doing a very simple max of an array function, because this is a pretty simple way of doing it. Because you can do things like there's ways you can avoid branches here and so on that are kind of cool, but at its core, it's basically just a loop faced a billion times before. So we got a main function here, right? And then we also need to define our data, which we'll do at the bottom. So this is going to be word, and I think I can say word, right? And then give it multiple words. So 0, 1, 2, commas. Syntax for half these things changes all the time between languages. So some of them have like you have to define multiple words in a row. You have to use like a different directive, and then you also have to like you can't use comma. You have to like just define like this, and it will interpolate what it means by basic spaces. Like it will figure out. Okay, so with these numbers here to loop through, we just need to find like a main loop. Right, that we're just going to loop, but then a main loop. And some people say like less than 10. It's also okay. We want to make it more readable. So in this case, we're just going to load into T0 1. This is going to be our I equals 1 register. Then we're just going to load a maximum into T1. This is going to be, I guess we're going to do a store words, which kind of sucks, but it's okay. So load word rather. So we're going to load from numbers. We're going to load 0. So the way I like writing load 0 is this. It's writing like this. You can write it like this. I believe you can also say numbers plus 0. Doesn't really matter. But because we're going to be looping through the set, it's kind of quite nice to basically have a pointer that we're going to increment. So we're also going to load the address into like a pointer variable, P2. This is going to be numbers. And so the reason why this is quite nice is because effectively we can just like increment this pointer and move it along rather than having to like have an I register. And we'll see that in a second, right? So in assembly, it's very inconvenient to use indexes to access arrays. It's much more convenient to use pointers that move up and down, because then you just basically have to load and store from that pointer, right? You don't have to like try to like compute the offset every single time. We'll do it both ways, but like it's annoying. So we're going to do this instruction here. So we have to first load this value, right? So we're going to load word into, I'm going to say T4, so T3, and then we're going to load word. Oh, why am I indenting this again? Load word T3, and then we're just going to load numbers of I. So the way to load numbers of I, if you're going to have to add a constant number to your numbers, and also by these indented, clearly I'm a bit tired. And so what we're going to do here is we're going to add numbers or add to T2 the offset. So we're going to say, for example, T3, 3, T2, and then add our offset here. And our offset is just going to be I, 0. So basically we're saying compute numbers plus I. And then what we're going to do is we're going to figure out an offset from that value. So in this case, it's just going to be basically loading that value immediately. So we just have to load from T3. We don't have to worry about anything else, right? So it's going to compute this offset here, find exactly what memory address represents our item, and then just load immediately from that. And we're just loading to the same register just for sake of convenience. The way I like writing these is I'll always put like 0 around it. And the reason why is because when I'm reading this really quickly, when I'm scanning through code, I want to be able to tell which things like are loaded or what, when I'm looking for like load and storage and stuff. It's nice to be able to just like read through it and recognize immediately that this is what you're loading from or this is what you're storing into, right? Otherwise, if you have something like this, like it's kind of hard to pick out the loads and the stores when you're just like scrolling through the code. And you'll find yourself, you get confused between like, is it loading into this variable or storing into this variable? And so if you just like always specify it, it won't change between load or store. It's kind of easy to say, okay, well, this is the memory address, right, that I'm accessing. So this is going to be the one I'm loading from or storing into, depending on the context. Anyway, then add 1 to I. Just a weird syntaxing I've picked up, and then just jump back to the beginning. And obviously we need to add a while loop condition, which we'll do in a second. But the while loop condition is basically branch greater than or equal to 10, I think, right? Yeah. So if T0 is greater than or equal to 10, go to main loop end. Otherwise, it's just going to loop forever. So what it's going to do is just increment through. Now we have to actually determine whether or not we want to set max. And so the easiest way of doing that is just to say that I have like a main loop continue. I'm going to say branch if it's less than equal. T3 is less than or equal to T1, which is our max. And jump to main loop continue. If it's not, we're going to set it. So we're just going to say move T1, T3. Basically, we're just doing this exactly here, right? So we're saying, hey, if this is less than or equal to this, then just skip it, right? Let's continue. And the way to write this slightly more succinctly is if I just copy and paste the entire thing. Using a pointer, I no longer need I. And so for that reason, I'm just going to update some of these addresses here. And so when we want to loop to the end, right, we still have to figure out when we want to stop, right? But the easiest way to stop is that we can just like load an offset. And we can say this is when we're stopping. This, right? And so as long as our current pointer is less than the end pointer, which is T2, then we can continue. That's like the easiest way of doing it. You could also have like some kind of like 0 terminator at the end. Like for example, in this case, you have like -1 to say this is the end of the array. Like a string kind of. Anyway, so we're looping all the way through. If ever at this point, our current pointer is greater than or equal to the last address, then we're going to stop. Else to compute, all we have to do is just load from it. And one of the benefits of doing something like this is that you have a lot less pointers. And we're going to load from a lot less registers. In this case, we had like, I guess in this case, it's going to be pretty similar actually. But like it can be a lot less because especially if you have like a string, you won't need this like offset here. All right, so we're going to load from this value, basically loading from our current address, T2, or T0 rather, pointer. And we're going to listen to T3 if it's greater than our max. Is last. Yes. I'm using because it's kind of like, and then we're looping through. then basically we're just like doing a dereference here of current. And we're saying, hey, if T3 is greater than, if current is greater than max equals current. And then to continue, all we have to do is just add 4, because each element's 4 bytes. And so this is a bit different from C and C and other languages like it. You can just go current plus. And so like this is really a void pointer, or basically a pointer without an actual like type to it. So what that means is that it's really just byte accessible. So we have to like increment the bytage, like how many bytes it is. Anyway, so using a pointer, that's okay. This is all fine. I'm happy with all this. So the next step is to do the same thing with strings. And this is just quite a quick thing, so we'll just do it. And then we'll look a little bit into Fibonacci, but we're really not going to spend that much time because you guys don't know functions. I think it would confuse you more if I went into like really great detail with it, but I think it's one case it's kind of useful and we can kind of show it works, and it's maybe needed for the lab. I guess we'll see. So the rough thing here is that we basically just want to print out the length of the string. We have a buffer here that represents the total bufferage of that string. And so what we're going to do is we're going to read in the string, and then we're going to figure out the length of that string, right? So this code here is actually pretty straightforward to use, but the nice thing about it is that writing it like this, it will require us to, because we're using a pointer, it's much easier because we don't have to like have this constant I access and increment I and so on. Anyway, so the first step is to basically just, if we copy and paste the code in, and then we can use it as a reference. There's other things you do too, like for example, I could put it side by side, I guess. Maybe that makes more sense. Maybe. Wk5 maybe? Yeah, here we go. And then max. Yeah, awesome. So what we're going to do here, basically is going to define P0 as being I, or in this case, P. We're going to define this to be buff. If it's just I, we'd also set I to 0 here. And we're just going to set T1 as, what am I doing? We're going to load the address of buff into T0. Say equals buff, right? And the next step is to loop provides less than length, which is kind of not that convenient, but not that hard, right? And the easiest way of doing that is basically just loading the address of 0, T1 of plus length, which is 1025. In this case, it'll actually be 1024 because we always want to write the /0 at the end, so we'll not include that in this calculation. And then we're basically just going to have main write loop, and the same thing with the end. And then all we're basically going to do is for every iteration, we're just going to check that branch greater than equal. If T0 is greater than T1, jump to main loop end. And main write loop end. And the way we can write this, I'm going to write this in the line above it, just because it's quite a long line, is saying if buff or P is greater than, right? And skip it. So we're using pointers. And then all we're going to do is just do a get char. A get char is pretty easy. Just a V0 set to 0, 5 rather. And then that's the way you really do, I think. Pretty sure it's 5. Let's just double check that. Yes. Oh, no, it's not. A char is 8. 12. Download 12 here. Get the character. I guess you could also say maybe, yes, but that should be fine. So we're just going to be loading 12 and doing a syscall. Then after that syscall, all we have to do is basically just check 0. You can, there's a special command like beqz to check if something is equal to 0. You can say beq as well. Then if so, we're going to jump to the end. But one of the nice things about MIPS is that when you're dealing with branches and stuff, these are the typical branches that you actually deal with. And the equal to 0 and stuff are just extra branches that you can deal with. In other languages, that's not true. In other languages like x86 and stuff, you always have to deal with like greater than 0 and less than 0 and equal to 0. So the way you do something like is equal to something else is you subtract them, or you do a test instruction, which does a subtraction. And then you check whether or not the result has the 0 flag set, for example. So it's kind of annoying, but basically there's no way that you can really compare things at equal value using like two instructions. So if this is equal to our instruction up here, t0, then we're going to jump to the end. Then the next step that we really have to do, so it's equal to 0, we jump to the end. And then all we really have to do after this is just try to actually access it, which is just going to be a load word, right? Just going to a load word. Oh, in this case, I guess it's a store word, isn't it? Just storing p. I am very flustered. So we're going to store into the address of t0. We're going to store we read. This is the character that we read from here. It's going to be loaded into v0, and then we're just going to store into a buffer. So it's just going to be like this, I guess. Buffer p equals c, right? And then the next step is just basically to the top again, right? And increment our pointers. Okay, so our pointers are single bytes. So increment by 1, and jump back up to the main loop. Yeah. It for this, right? All we need to do at the end is to just do this increment here as well, right? Which is luckily pretty easy. We can basically just say store word 0 into t0, right? It's kind of the same thing as saying equals 0, which equals /0. So you could also like do a load temporary into this address, so then from there, do the LUI, and then load push that in. That's okay. So the next step is to try to find the length of the segment. So that's pretty straightforward. Length calculation is basically just create a pointer pointing to it, keep going while the value at this address is non-zero, because /0 is going to equal 0. So while the value is non-zero, just keep incrementing it down, right? So the length here will be basically just load address 0, buff, then load the word. So load byte, because it's going to be and this should also be load byte, and this should also be load byte because we're loading singular bytes for each character. And we're going to load those into T1. Then branch if equal to 0, like the end, right? And so effectively, we're looping over and over again, and we got the EOF call, which is what this is. And the same kind of thing happens here, but in this case, we're checking for /0. If it isn't equal to /0, then we're basically just going to increment a counter by 1. Right? So we're just going to have some kind of counter that represents length up 2, and we're just going to increment the counter by 1 each time. The other ways you can do this too, for example, a very easy way would just be to find the subtraction. Yeah, find the difference between where buff ends at and where it began at. So you could just do like a subtraction command. Say like this is the length, it's going to equal to current position of buff minus buff. So this way you'd be subtracting buff from t0, which would find the length of the field. So it'd be like how long it is. And then we're jumping to raw. And then obviously here we probably always want to jump instruction back up. So you can see that pointers, this becomes quite simple. And we're just like moving pointers along. We still have a counter, but we don't have to use it. Whereas if we had to actually use indexes, we'd have to like add to buffer every single time and like find the offset it actually is, and then access it. And it's just like it's more instructions. It's up to you. But typically computers do prefer the pointer method, and in a lot of cases the moving pointer. It's just a bit simpler for them. I think it also makes more sense, but again, it's up to you. If you want, you can do indexes just like what we did with the previous one, right? Originally, and I'll include the code for that as well, so you have both of them. I'll include some code as well for this one in this method as well. I had some from a previous year I wrote. It's pretty straightforward. It just requires a bit more. Basically, you just have to like add to the next time. And then the final thing we're going to go through very quickly is fib. Just so when you see it in the lectures this week, you can kind of understand it a bit quicker, because I'm pretty sure he's going to go through it pretty quickly, because he's kind of behind it, obviously by like maybe a single half lecture or something. So it's not that much, but I presume he wants to try to catch up. And so it's probably decent to have a decent understanding. And we'll come back and we'll look at this stuff later. The linked list, that'll be next week, which is quite a fun thing to do. It's a little initially annoying in some cases, but one of the nice things about it is it just kind of works out in the end, and you get some really cool behaviors. Like you get function pointers. For example, here we look at like function pointers of this application method, right? And I've added the register command just to indicate these are registers. In reality, this actually means something different in C. It's similar, but not the same thing. So this Fibonacci method here, I always define my Fibonacci like this. Some people define it differently. It doesn't really matter how you define it. I just define it like this because it means that you don't have a sequence that's like 0 followed by a bunch of ones. This sequence here is kind of really annoying to do algorithmically. You basically need another branch, which kind of sucks. I mean, you don't have to. For example, you can say if I is less than or equal to 1, and that would work for this. It's just like it's less readable, I think. So I just preferred using this format. They're both identical, really. So in this case, we're just going to check, and the way we're going to do this recursion, this kind of function call, right, is we're going to abide by a very simple rule, which is that our argument's going to be an A0. So n is going to sit in A0, and we're going to return the value into V0. So it's going to be like either return 1 or return fib of n minus 2 plus fib of n minus 1. Right? So effectively, that's all we really have to care about initially. So if we do this first statement here, our function call is very simple, right? I'm going to call this simple return down at the bottom. It's because we want to do a more complicated thing, so it's nice to have just a simple return, right? So what we're going to do is we're going to branch less than equal. So if n, which is A0, is less than equal to 1, right, then branch to simple return. And the strategy here is that we're basically doing this very simple if case here, and this is a very simple statement, so we don't have to do really anything special about functions. All we really have to do is basically just load into V0, 1, and then return, right, from that function. Nothing else really has to change here. And this is all we really have to do for the simple case. It gets a little bit more complicated when we actually want recursion. And the reason why it gets complicated is because we have to use the stack. Right? And I don't know how much of the stack you've covered. I presume you covered a little bit of it because you've done main memory. The stack is something that grows down. So what that means is that you can subtract from the stack, push something onto it. You can add to the stack, pop something off. So we've just clarified here that the return value has failed. So what we have to do is we have to save some variables because we're going to be calling a function again. So the way it works in MIPS, right, is that functions don't exist, right? There's no such thing as a function. This is just a label. So all we're basically going to do is we're just going to jump back to the label and do the exact same code again. But this time we're going to change n. So you can kind of think of it as becoming a while loop, right? Effectively, we're kind of doing something like this. We're putting like this kind of big while loop in front of it, something, and then we're basically just processing this code here for n. And if we get to the stage where the else is true, a bit harder for fib because it's not tail call recursive, so we can't actually make it a while loop. But if it was, it would be a bit easier to kind of show this off. But basically changing what the value of n is, right? Looping this entire loop, and then we're going to come back to this statement here, change it again, loop back around, and then come back to the statement again, and then process the same thing over and over again, right? So it's kind of becoming like transforming the idea of what the function is becoming. So the way we can do this is pretty straightforward, luckily. So because we're going to be calling a function, you always have to save var. The reason why we have to save var is because Egyptian. No. It is because var is used to determine what the return address is. So if we're going to be calling a function, we're going to have to tell that function where to return to, right? Like if we're calling fib again, this jump return address needs to be like here, right? To process the second call. So what that means is that we're going to be changing what the return address is, and it's a global variable. Which means if we're going to change it, we need to store the old value somewhere so we can actually return. Because otherwise, how do we return from this function if we're changing what the return value is or the return address is? So we're going to store the return address, right? Save raw. Okay. Then we're going to do the exact same process again, right? But for other variables that as we need them, right? So right now we don't know what variables we need, so we're just going to keep it like this. But I already know we'll need one for n, right? Because we're going to be just doing subtractions with it, and we'll need one for the result here, right? So the strategy here is that we got to figure out what variables we need. But also the strategy here is that the SP goes down, right? So the stack shrinks downwards, right? So what that means is that as we push things on, we're moving the pointer downwards, and then as we're popping things off, we're adding the pointer upwards. It's basically just one big array, right, that we're just accessing. But the array is indexed by a pointer that we're moving up and down. So what that means is the very end of our program, just before we return, just after we do everything, we have to also restore these values back to the original cases. And now luckily restoring is super easy. All we do is we copy all the values across and we swap the lines. So keep in mind that we have to do this in the opposite order. So for example, as we'll need in a second, we want to store a0, right, for our argument n. When we want to restore it later on, you basically want to do the exact same arguments. We have to like flip a store word to a load word, for example, right? Load word, and then the add becomes +4 rather than -4, right? But it's still the same process. As we're accessing these things, we're going to do them in the opposite order that we push them on, right? Just like a stack, it goes the opposite order off, right? So the load word swap with the adds. So we go add, then store word, add, then store word, load word, then add, load word, then add, right? And also the order changes. It's really important to get this order right, else your program just won't work and will crash because you'll load a wrong address for raw, and then you'll jump to that address, and then the program just won't work. So the trick here is to always make sure the order is the same and opposite, right? Which is one of the reasons why I like doing it this way. Even though this is more code than the frame pointer that you'll learn later on, it's simpler and it's also easy to verify very quickly by just looking at it. Right? It's up to you though, both valid. So the strategy here is to basically then figure out the first Fibonacci value. So we're going to figure that out right now. And we're just basically going to subtract 1 because we're doing it like this rather than like this. It doesn't matter how we do it. I'll just make it keep to the code standard. So it's all the same, just so it makes sense when you compare it. So basically we're doing, these are not indented correctly. I think it's meant to be like this. It doesn't really matter, but you know what, we'll keep it. This is going to be fib of n-1. So then we're going to do a jump and link. So effectively what we're saying is we're saying, okay, we're going to change what n is, and then we're going to call Fibonacci again. We've changed what n is. So when we call Fibonacci again, n is going to be different, right? Because we've just changed it. So it's now going to process the entire thing again for n-1. Now, JAL, or jump and link, what it does is very straightforward. It does a jump. Right before it does a jump, it does basically a LI. So LA, raw, based on the line immediately after the jump. So it does this, right? It's going to load the line immediately after the jump into raw, and then it's going to do the jump for fib. So when fib returns, it's going to return right here. This is a bit easier than adding a bunch of extra labels, right? There's other ways you can calculate too, probably dynamically, but this is fine. So next step is to basically grab the return value from this function and to save it somewhere. We have a problem. If we want to save this value, right? How do we save the value so that the next time we call a function, it isn't overridden? And this is again the strategy why we use S registers. So S registers are saved registers, and the rule is before you touch an S register, before you touch it, you always have to save the old value, then always have to restore the new value. Then like save the old value, then restore it later on. Right? This is going to be a fib of n minus 1. So the strategy here is strategy way too much. The idea around this is that before we can be allowed to touch the S0 register here, we have to save the old value. We don't have to save the value up here. We could save down here. It's just style reasons why it's better to put only like one load word and store word and keep them all at the very top. And often I'll compact this into a series sequence of lines like this, rather than keeping them separate, just to like save space. Up to you how you want to visualize them. And you can obviously, what you could do is you could use structure offsets. So what you could do is you could keep this as -4, then -8, and -12, right? And then just do one add at the very bottom, rather than having to do all these adds. Right? I'm not going to do this, like in the actual code, I'll remove it in a second. The idea is that you're able to access all the stuff like this. Anyway. So the next step is to basically call the function again, right? But we can't just like add 1 to A0, because when we call a function, that function may also subtract 1 from A0. They may all subtract 1 from A0. We may lose the value of A0. Now we could try to be clever and try to like restore the value of A0, right? As it's going to restore it here, right? But it's probably just much easier just to restore the original value that we had all the way up here, right? When we store here, then just load it. Rather than trying to be tricky and just add 1 to A0, right? It's just try to keep it simple, right? We're just going to load A0, right, from our stack pointer. Now, the problem here is that we need to find an offset for our stack pointer. In this case, it's going to be +4. The reason why is that this is 0 and this is 4, right? It's kind of inconvenient because if we had another stack insertion down here, then this would have to be 8, right? So this changes over time, and that's the whole point of having a frame pointer. Because a frame pointer means that these values don't change, and you have this one pointer that points to this value of the stack at the very top of the function, and it doesn't change throughout the function. So as the stack grows and shrinks, it stays the same. So that way you can refer everything relative to that. Right, so then we have this, and then all we're going to do is basically just load restore RA. So we're just going to say n equals original value. Then we're just going to do an addition, or in this case, a subtraction by 2. Right? And then we're just going to call the same function again. Again, we've stored our A value here, our raw value. So when we come back to it, it should be okay. So now we've come back to it, all we have to do, add V0 and S0. Right? We're going to store that into V0 because this is a return value. Okay. So let's kind of recap this line here because this one's kind of confused. So the first thing that's confusing about it is that we're accessing S0. And you go, why can we access S0? Because when we call this function here, it's going to modify S0 based on this, right? And the reason why we can access it is because every function will save the old value of S0. So when it restores the old value of S0, as we can see here, the value it will restore will be our value. And this is the whole point of saved registers, is that you can use them throughout your program and never have to worry about like restoring them and saving them, as long as you restore at the top of every function, a save and restore at the top and bottom of every function. So basically, if every function saves and restores the old values, then each individual function doesn't have to like worry about like, oh, okay, I have to save S0 before I call this function, then restore the old value after the function, because most likely the function is going to change it. Like, that's messy, right? If you use T registers, for example, and you want to save a T register, then you kind of have to do that. You're going to have to do something like this to save a T register. You know, okay, I'm going to call this function, so I'm going to save T0, which could be whatever, right? Maybe whatever value you want. And then at the end of the function, you have to load it back in, because we don't know if the function could have modified it or not. It's kind of inconvenient that way. Okay, so that kind of makes sense. So the whole point of functions is that they're kind of just like big loops, right? That you're just looping over and over again, right? When it's recursive. If it's not recursive, then I guess it's not really a loop, right? You're just jumping to a separate part of your program. It's just like one big function with a bunch of smaller sections. Hopefully that made sense, and we see it more in the lectures. So if it didn't, don't worry. But the base idea behind functions and recursive stuff in MIPS is that they use the stack quite I cannot say that word, quite extensively. And getting good at the stack is useful, but at the end of the day, you can just do this over and over again, and you don't have to worry about using like frame pointers or anything like that. And in reality, if we're looking at like quotation marks like real code for MIPS, it gets even more confusing because you have things called